to introduce Melanie Weber from Harvard University. And she will talk about discrete curvature and applications in graph machine learning. Thank you very much, Melanie, for being here.
Thank you very much for the introduction and for inviting me. I'm very sorry that I couldn't be there in person. It was hard to arrange with other travel, but it's been a really great conference. I've been able to join virtually for some of the talks, and it's been a really great week so far. So thank you for having me. The talk today will be in flavor more similar to Soledad's talk from yesterday than some of the others, where it's not about using AI to discover new mathematics or to assist in improving new results, but in using tools from pure mathematics in machine learning. And in particular, in this talk and in my group at Harvard in general, the main sort of area of mathematics where we take our tool from is differential geometry. So you already see the term curvature in the title. And in particular, today, we want to talk about how we can use classical notions of curvature and their discrete analogs in graph machine learning, so to perform machine learning on graph-structured data. Before we get into the mathematics, I want to just briefly motivate what are the kinds of learning tasks, the kind of applications where we might want to use such methods. So the talk itself will be very methods focused, so you won't see too many applications, but just to preface that with the kinds of problems and applications that you can have in mind throughout the talk. So in graph machine learning, we learn functions, we learn models that are defined either on collections of graphs or on the nodes of an input graph. And the sample tasks that you see here are of these two forms. So you see, for instance, graph classification. The example here is a graph classification task on molecules, so in the biochemistry domain. And here, the input of our model would be a collection of graphs, each of which represents the chemical structure of a molecule. And we want to predict the properties of those molecules. That can be something like toxicity or how effective a certain molecule is in a drug. Then another example that you see is node classification. So here, the input is a single graph. And in this example here, each node in our graph represents the user of, let's say, a social network. And then we want to predict which of those nodes are humans and which are bots. So what are real users and what are synthetic users? And we want to assign labels accordingly. We can do that in a supervised way if we have some partial labels. So if for some of the users we know those are definitely humans, and maybe for some of them we know those are definitely bots. There are also other graph machine learning algorithms that one can use if there's no prior information, such as community detection, for instance, which would be an unsupervised algorithm. And then to give you a third example, that is for link prediction. So here again, our input is a single graph where the nodes represent, in this example, drugs. And then we have a few edges given. So for some pairs of drugs, we know that there is an adverse reaction. And then we want to predict new links, new edges. So predict for which other drugs we might expect to see an adverse reaction. Okay, so those are the kinds of problems, the kinds of application that you can have in mind throughout the talk. And we want to discuss algorithms for solving problems like that. And the mathematical tool that we will see throughout the talk is a discrete notion of curvature. Now, most people in the audience are probably pure mathematicians, so have some training in pure mathematics. So you've probably seen concepts of curvature in differential geometry. Since we're here working in the discrete setting where our input is graph-structured, so a discrete structure, we need to define sort of new notions of curvature or analogs of classical notions of curvature that can be defined in this setting. We will mostly talk about graphs and networks and a little bit about point clouds, but you could think about similar ideas on more general discrete structures that you sometimes encounter in applications such as hypergraphs, for instance, simplicial complexes, polyhedral complexes, CW complexes, and so forth. And then just to briefly overview, and then we will later go into details on these applications. What are the kinds of algorithms where we can use notions of curvature, and how can we use those notions of curvature? So we mentioned briefly already community detection. So this is basically a shallow graph machine learning method. So one that doesn't use graph neural networks or ideas from deep learning, but it's a classical graph learning algorithm. The idea here is very simple. So if we look at that cartoon, for instance, here we have a graph that has densely connected substructures that have sparse connections in between. We have no labels given up front, so we don't know this like red, blue, and green annotation here we have not given up front. And just by the structure of this graph, where we have dense and sparse regions, we want to recover these clusters. So that's the task of community detection. If we are in this setting where we have these nicely separated communities, there are lots of algorithms for doing that. It's a bit more harder if we are in this more realistic setting where the communities are actually overlapping. So there are some nodes that are in part of different clusters, so to say. And there's one line of work on curvature-based algorithms that uses the curvature of a graph to recover these structures. So we will see this later on, that curvature can tell us something about very densely and very sparsely connected areas in the graph. And we can use this observation to identify community structure. I'm not going to talk about this in detail, but I put here some references of recent work by my group and also by others on these algorithms. What we will talk about today is using discrete curvature in the context of graph neural networks. In particular, while graph neural networks, I will introduce graph neural networks later on, just as a preface here. While graph neural networks generally work really well, including for the 3 tasks that we've seen earlier, there are some limitations in representational power. So what kinds of functions classical graph neural networks learn, and then sometimes also challenges that arise in the training dynamics, so-called oversmoothing and oversquashing effects. And it turns out that taking the geometry of the graph characterized by curvature can help us to mitigate and sometimes to overcome some of those limitations. So we will discuss that in detail. And then the last application that we want to look at, here the input is not necessarily a graph in itself, but a point cloud from which we construct a geometric graph. And then a natural question that we can ask in this setting is if the geometric graph that we have constructed has some sort of spatial information about the underlying space from which the point cloud was sampled, and we compute the curvature on that graph. Does that tell us something about the underlying space, about the underlying manifold, and does that allow us to learn something about the data manifold, and then what kinds of applications could that have? So that's a third topic that we want to discuss in this talk. Before we get to those 2 applications, I want to briefly introduce the notions of curvature that we will be discussing here. So if you haven't seen much discrete differential geometry before, those might be new to you. And then we want to focus on the 2 application areas that I briefly previewed. So using curvature tools in graph neural networks, and then thinking about continuum limits of curvature and how we can apply that in machine learning. Okay, but let me start with notions of curvature. So if we go back to differential geometry, we don't have to sort of repeat here in detail how notions of curvature are defined in discrete differential geometry. If you've seen this before, you know that most of the curvature notions that we use in differential geometry derive or are characterized by the Riemann curvature tensor, including Ricci curvature, which is the curvature notion that we will see in this talk. And then just to sort of repeat intuition, of course, you've seen this before. So if we're in the Euclidean space, like in this cartoon here, then we have flat curvature, right? If we are on a sphere, we have positive curvature. And then if we are on a saddle-like surface like this, that would be an example of a negative curvature. Now, in the discrete setting, if we go by this intuition and look here at how this tensor is defined, we see here a differential structure, right? Which, of course, we don't have in the discrete setting. So it's not immediately obvious how we would even define a curvature notion in the discrete setting if we now think of being on graphs, right? We can't take the standard notion from differential geometry and translate that one-to-one to discrete setting. We don't have the differential structure. The space, the mathematical tools in that space looks very different, so we can't just map that one-to-one. What we want to do instead is to use curvature analogies. So we want to look at what are other properties in the continuous setting that we can link to curvature. And maybe some of those properties already have a translation or an analog in the discrete setting that we understand well and that we maybe have already studied mathematically. And then can we define a curvature notion that preserves the relationship with that property? So this is what we will call curvature analogies, and we will see two notions of curvature that derive from a different analogy. Those two curvature notions is a biased selection of me. So there are many other discrete curvature notions that have been proposed. None of them really recovers the full information that curvature gives you in the classical setting. So due to this way of defining curvatures via analogies, we usually preserve some properties but lose others. So in practice, we would choose whichever curvature notion preserves the properties that we're most interested in. And in my work, I'm mostly studying the two notions that I will tell you about, hence the biased selection. Okay, so just to like very briefly state here what kind of notion we are using. So I already said we will be using Ricci curvature. So Ricci curvature is sort of one part of the Riemann tensor. It describes a local notion of curvature that can be seen as a local average of sectional curvature. And what it measures is basically geodesic dispersion. So it relates to the growth rate of a volume ball. So this locality of Ricci curvature is a good starting point for defining a curvature in the discrete setting, because in the discrete setting we also have sort of like very straightforward way of sort of measuring locality, right? If we are in a discrete setting and we look at let's say one edge, then the sort of local neighborhood of an edge is kind of naturally given by looking at the neighborhoods of the adjacent edges. So that introduces a sort of very natural sense of locality. So translating a local notion of curvature like Ricci curvature seems pretty intuitive, and that's also why those notions I believe were first used to be a sort of a basis for translation to the discrete setting. The first notion that we will see goes back to Olivier, was introduced in 2007. And here the curvature analogy that is built is between the behavior of random walks and the local curvature. So if we're in the continuous setting and we start two random walks at nearby points, then if the manifold is positively curved locally, then the two random walks will draw together or at least stay close by with high probability. But if the manifold is locally negatively curved, then we sort of have an expansion of space, and then it's very likely that the random walks will draw away from each other. So this is something that one can prove in the continuous setting for the standard notion of Ricci curvature. Now, if we are in a discrete setting, random walks on graphs is something that's been studied for a very long time and something that we sort of as a community understand well. So if we now look at this same behavior of random walks on graphs, what we could do is, let's say if we want to find a geometric characterization of this edge that's in the cartoon here shown in red, we can look at the two adjacent nodes, U and V, and then start a random walk at each of them. And then clearly, and let's say for simplicity, this is an unweighted graph, and we just perform uniform random walks. So with probability 1 over the degree, we jump to any of the neighbors. Okay, so standard uniform random walk. So if we start uniform random walks on U and V, and if their two neighborhoods are overlapping a lot, then it's likely that the random walk will stay, that the two random walks will stay close by. Whereas if there's very little or no overlap between the neighborhoods, so no joint neighbors, then it's much more likely that the two random walks will draw apart. And this behavior of drawing apart and staying close, that is something we can measure by looking at the Wasserstein-1 distance between the two measures that the random walks induce. So to compute the Wasserstein-1 distance, we solve like an optimal transport problem between the two measures. And then Olivier suggests the following notion of curvature for such a edge here. He says that we look at the ratio of this Wasserstein-1 distance. So clearly that Wasserstein-1 distance is large if there's not much overlap and the two walks are drawing apart. And it's small if there's a lot of overlap and the random walks are staying close by. In an unweighted graph, this d sub g here is the shortest path distance on the graph, so this is just 1 in an unweighted graph. And then you see if we look at 1 minus this Wasserstein-1 distance between the two measures, then this is negative if the two random walks are drawing apart, and it's positive if the two random walks are drawing together, which means that this notion of curvature preserves this relationship, this analogy in the discrete setting. Okay, so that will give us one notion of curvature that we will see throughout the talk extensively. I want to briefly mention a second one, which is sometimes you sometimes also see in applications, and that's Foreman's-Ritchie curvature. So that was introduced by Robin Foreman in 2003. And that derives from a completely different curvature analogy. So here, going again back to differential geometry, in differential geometry, we have something called the Bochner-Weizenburg relation, which gives us a connection between the Laplacian and the Ritchie curvature. And then Foreman's idea was to define a discrete analog of that Bochner-Weizenburg identity in a very general discrete setting. So for CW complexes, which of course then can be specialized to graphs, for instance, or simplicial complexes or other discrete settings that we're interested in. And the key idea here to get around this missing differential structure in the discrete setting was to define this with respect to the boundary operator that we can define on CW complexes. So that essentially replaces or is a discrete analog of the differential structure. And then if we now specialize to the graph setting that we are interested in here, so in the graph setting, we understand the graph Laplacian and its properties already really well. Right, so we can define a discrete curvature notion that is consistent with the graph Laplacian in the sense of the Bochner-Weizenburg identity. And that's where Foreman's discrete notion of curvature comes from. What I have written out here is how this notion looks like in the case of an unweighted graph, just so that you see here how it's computed or what are the types of combinatorial information that goes into computing this here. So here you see, for instance, we take into account the degree of the adjacent nodes. So again, here, if we look at the red edge, right, we have adjacent nodes U and V, and then we count their degrees. And then we also take higher order information into account. So for instance, if we have, if that edge is part of a triangle or part of a quadrangle, or maybe multiple ones. So we count these higher order structures that the edge participates in, and that gets factored into the curvature notion. So we have two curvature notions. One derives from an analogy with random walks measured via optimal transport, and the second one builds an analogy between the connection of curvature and Laplacians in the discrete and continuous setting. The two notions, I should say, are sort of measure similar properties also in the discrete setting. So even though they derive from very different analogies, if we measure, for instance, where in the graph we have high versus low curvature, that is usually consistent between the two notions. And there are also some nice results, for instance, the one I'm citing here by Jost and Munch that built theoretical connections between those two notions of curvature. From a computational perspective, as you might already imagine when we looked at the definition of Olivier's curvature, in order to compute that, we have to essentially solve an optimal transport problem for each edge. That's something that can be prohibitively expensive to do in practice. Right, if we solve, so in the discrete setting, the Wasserstein one distance is the Earth mover's distance, and computing that, for instance, with the Hungarian algorithm has a cubic complexity in the maximum degree, right? So that's clearly very expensive, but there are ways of computing faster combinatorial approximations. For instance, this one proposed by us last year that drives down this complexity and can still give us a good approximation of the curvature. So sometimes in practice, these workarounds are necessary to make it scalable to the kinds of graphs that we encounter in practice. Foreman's curvature, on the other hand, since it only aggregates combinatorial information, it can be computed much simpler. So that the notion that I've shown you, if we restrict ourselves only to counting triangles, which is usually enough, then this is maximum. This is linear in the maximum degree. So that's of course much less expensive than computing Olivier's curvature exactly. So that's just as a summary of the two curvature notions. And yes, what you should keep in mind. So Olivier's curvature, if we compute it exactly, is slightly more expensive, but also has a sort of better understood theoretically. So sometimes that rich theory can give us some additional insights. And then Foreman's curvature derives from a different analogy, is more or less consistent with Olivier curvature and a bit more efficient computationally. Okay, so with that, with those two curvature notions in mind, let's now move on to how we can use those notions in the setting of graph neural networks. So graph neural networks, if you haven't seen them, is essentially our way of building a deep learning architecture on graph structured data. So we've already seen the two kind of effects that we want to analyze. But before we get to that, let me just remind you what graph neural networks are. Many of you have probably seen this, but just so that we are all on the same page. So as was already said, graph neural networks build essentially a deep learning architecture on graphs. And the key idea behind most graph neural network architectures is so-called message passing. And message passing, or one layer in the graph neural network, are characterized by two functions, an aggregation function and an update function, that we want to briefly review. Before we get to that, just a note that in general, when we use graph neural networks, we often assume that the graph is attributed. So at input, we have not only the adjacency of the graph given, so which nodes are connected by an edge, but we have also features given associated with each node in the graph. And then those attributes in the input graph are used as initializations of the node representations, which we learn through message passing. So this is written over here. So H sub V will denote the representation of the node V, and at initialization at layer 0, so to say, we initialize that with the attributes in the input graph. And then in each iteration of message passing, each layer, if you like, we update those representations as follows. So at a given node, we look at its neighbors, and then look at the representations of those neighbors and aggregate them into a multiset. And then that multiset, together with the current representation of our node V, is put into an aggregation function. And that aggregation function outputs some sort of aggregation, some summary statistic usually, of this set of representations. So that could be something like a mean or a max, so some form of aggregating that information given in the multiset. So that gives us a message. And then that message, together with the current representation of the node, is put into an update function. And that update function is a trainable function, usually like an MLP. And that outputs the updated representation. Okay, so basically we use in each iteration, we update the representations of our current node with information that's given on its direct neighbors. And then we might perform several rounds of this, so several layers, if you like. And then at some point, we output the final representations. And if we are in a, so those are given on the node level. And then if we perform a graph level task, we might globally aggregate them. So this is what the message passing graph neural network does. So now I've already mentioned while this works very well in general, there are some issues that can arise here in those message passing dynamics, and that have to do with the graph's geometry, with the graph's topology. So two effects that are often cited in this context are so-called oversmoothing and oversquashing. So if we start with oversmoothing, so if you think about how message passing works and how information is locally aggregated, and let's say we're now updating the representation of a node in a very densely connected area of the graph, right? Then in each iteration, we aggregate information from the neighbors, we compute some summary statistic of that, and then update the representation. And then we do that for several iterations. And the kind of information that gets aggregated here in each round at neighboring nodes is essentially the same, right? Because the graph is so densely connected. So the nodes share a lot of common neighbors, so most of their neighborhoods are overlapping. So that means that after a couple of layers, the useful information that was maybe given in the node attributes at input gets sort of averaged away, right, and gets lost. And that's, in this context, what we call oversmoothing. Now, since that occurs in regions that are very densely connected, those regions are typically characterized by high curvature, right? If you think back, for instance, how we defined Olivier's curvature earlier, clearly, if we compute Olivier curvature of an edge and in this densely connected region here, that's going to be positive. The second,
sorry, just to make sure I understand. How would we view, for example, a transformer as a graph neural network? Would it be, let's say it has only one head.
I'm talking about message passing graph neural networks here.
Okay, yeah. So I'm saying, for example, let's take would, for example, a transformer be an example of a graph neural network?
No. A transformer is not a message passing graph neural network. Like, this is not the architecture we're looking at.
Okay. So in this graph, should I think of every edge as having some sort of feed-forward neural network layer?
So I'm sorry. So this is the architecture that we're considering. I'm not talking about transform. I'm talking about a standard message passing graph neural network here. And then the representations get updated as we just discussed. Right.
Okay.
So at each node, I take the current representation of the node, and then the representations of its neighbors. I aggregate that into a multiset, and then this aggregation function, let's just say, computes an average. Okay, that would be one simple way of aggregating. So it computes an average, and then if I do that a couple of times in a densely connected region, where essentially this multiset that I'm aggregating here is essentially the same, because the neighborhoods are overlapping, then I just keep averaging the same information, right? And then I'm losing information clearly.
Okay.
So
if I take something like just a standard feed-forward neural network, some activation function, would that correspond to a graph which just has bivalent vertices, one after the other, without any trivalent vertices?
So I'm here. My data, the input is a graph. Right. This is not. I'm not analyzing a neural network.
Okay. So
the input is a
data structure.
So a graph neural network means that the input is graph structured. So the input is either a single, in this case, let's say the input is a graph, and then I learn a representation of that graph. Right. So training a neural network as an architecture, it's a separate thing.
I see. So this is just about the structure of the data.
No, I'm talking about the learning algorithm, but I'm not talking about like you're trying to connect this to like a standard neural network, but I'm really talking about learning algorithms on graph structured data.
Okay, so the graph just refers to the data structure.
So
the structure.
So let's say it's a social network. Let's say it's a social network. Okay,
Yeah,
so at
right.
input, let's say my input graph is a social network. Each node is a user. And then the attributes are maybe, I don't know how many followers this person has, where this user lives, how often they are online, right? So those are attributes at input. And then I'm now learning a representation of that graph. That is the learning task.
But this aggregation function is sitting on a node, right? This message is passing an aggregation. It's happening on a node. In a node, yeah. Okay, it's happening.
I learn a representation for each node. So I do this for each node. I learn a representation of each node, a vector associated with each node.
You choose master node for every iteration.
Okay.
I can't hear very well what's going on in the audience. I think I'm gonna move on. Is that okay? We can take more questions later.
Yeah, sure.
Okay. Yes, so we were talking about oversmoothing, which arises in region of the graph that are very densely connected. Now the sort of opposite and that are characterized by high curvature, right? To bring in curvature here. So now to talk about the complementary effect in a sense, oversquashing. So oversquashing would in a graph that's like this simple cartoon here, occur on an edge as the one colored in blue here. So imagine you were to perform message passing along this edge. So let's say maybe you were updating the representation of this node over here. And then information gets aggregated from its neighbors, right? And then layer after layer, we sort of see technically information from further away neighbors in the second layer from the 2-hop neighborhood, or an aggregate of that information, and the 3-hop neighborhood in the third layer, an aggregate of information given in the 3-hop neighborhood. But if we have this sort of single sparse connection between the communities here, then what this means is that this node, and in fact all nodes over here, will only ever see a summary statistic of the information that's given over here, right? Because we only ever sort of pass an aggregate of the information over here through to the nodes in the other community. So that means we have, in a sense, a bottleneck in the message passing, and that again can lead to a kind of information loss that we might not be able to afford if the downstream task that we eventually want to solve relies on long range dependencies in the graph, so information between nodes that are not direct neighbors, but sort of longer paths along the graph. So this is a second potentially harmful effect that we need to take into account if we train our graph neural networks with message passing. And importantly here, again, bringing in the geometry of the graph, those edges where we expect to see those bottlenecks form are characterized by low curvature, in fact, the lowest curvature in the network, right? Because the neighborhoods of the adjacent nodes in this case are completely disjoint. So if we start a random walk over here and a random walk over here, they will clearly proceed into the respective communities and will clearly draw apart with very high probability. So this sort of characterization of where in the graph we see oversmoothing and oversquashing, that can be characterized with both Olivier's and Foreman's curvature. So this low versus high curvature, that's true, no matter which curvature notion we would use. So one can make this precise. This is what I just explained heuristically, but in the interest of time, I'm skipping over that. So believe me that this characterization of low and high curvature is actually something that we observe. And let me tell you about how we can mitigate or maybe overcome this. Right. So in order to avoid oversmoothing and oversquashing effects, one thing that we could do is to say that we don't take the input graph as is, but we perform some perturbation of the input graph as a pre-processing routine, and then perform our message passing on this perturbed graph. And in particular, if we were to remove some edges in the very densely connected areas.
Do we even try to remember the modifications, or we just let them? Do we even try to remember how we modify the graph?
Let me just explain how the algorithm works. Okay, before I think it will explain. Okay, so the idea is to perform as a pre-processing routine perturbations of the input graph. Okay, so in regions that are very densely connected, we want to remove a few edges. And then in regions where we have very sparse connections, we want to add some edges in a sense to ease the bottleneck in the message passing. Now, of course, we have to do that very carefully, right? If we add and remove too many edges, then we change the information in the input graph. And then, of course, the representations that we learn will not be particularly useful in downstream tasks. So we only want to perturb like very few edges. We do not specifically keep track of which edges are synthetic or which edges have been removed. So we really treat this as a pre-processing routine, perform this perturbation of the graph, and then train the graph neural network as usual. So the removing edges and now bringing in the curvature. Curvature, in fact, allows us to evaluate. So this comes from the theory that I just skipped, but essentially curvature allows us to quantify what is too high and what is too low curvature. And in fact, if we compute the curvature for each edge in the graph, we get in graphs that exhibit these effects, we get a curvature distribution like this, where we sort of have a separation between the low curvature edges that form sort of sparse connections between densely connected areas, and then the curvature in the densely connected area. And then based on this distribution, we can sort of learn from this distribution thresholds for what is too high curvature and what is too low curvature. So what we do in the pre-processing routine is that we add parallel edges everywhere where we have too low curvature. So if this is a sparse connection, right, we look at some of the neighbors and then, for instance, add an edge here and an edge here. And then in the densely connected areas, we cut away all edges that are above this threshold. And again, we can do this both with respect to Foreman or Olivier's curvature. We get a similar distribution in both cases. What you see here is Foreman's curvature in this case, but it could be done with either curvature. And then one reason why you might want to use Foreman curvature here is, of course, the scalability. But you could do the same with with Olivier curvature, and the theory that gives you these thresholds also can be derived for both curvatures. I should say here that curvature is not the only proposal for this perturbation, which is often called rewiring. So there are other proposals for doing this that use information on the spectrum of the graph Laplacian, for instance, or various other properties of the graph, like effective resistance, for instance. But what makes curvature particularly useful for computing these perturbations is that we have this this guideline of where to add and remove edges, and to do this in the right amount. whereas in the other methods that tends to be done via hyperparameter tuning. So which edges to be added and removed is something that's optimized over grid search, which of course makes this preprocessing routine very expensive. Which is of course not what we want in practice. We want this to be as efficient as possible, because we then still need to put all the effort on in training the actual network. And I also put here some small set of experiments for training here a graph convolutional network. So one instance of a message passing graph neural network on some graph classification tasks. So those are similar to the biochemistry test that we talked about earlier. And here the two columns that are highlighted in blue are doing this rewiring with Foreman's curvature, and then this is what you would get without any of the preprocessing routine. And then this one, for instance, is a spectral rewiring. And you see here that in almost all cases, this curvature-based rewiring and using the guidance from the overall curvature distribution, it does give us a boost in performance in downstream tasks. Okay, but let me move on to the second effect. So we have already said, and I think also Soledad mentioned that briefly in her talk yesterday, we have to be careful with the expressivity of geometric architectures like graph neural networks. In the context of graph neural networks, that is a topic that's been studied a lot related to the representational power of graph neural networks. So thinking about what kinds of functions can a graph neural network learn and what kinds of functions can it not learn. So this is really in the context of graph neural networks. There are many even simple functions, like what is the diameter of a graph or what is the largest cycle of a graph, that the standard message passing paradigm that I showed you earlier, graph neural networks that implement this cannot learn. And I want to briefly motivate sort of where this is coming from, or what are the kinds of limitations that we see in practice. So in order to measure the representational power of graph neural networks, the task that we usually use to as a reference point or as a benchmark is graph isomorphism testing. So if we have two graphs, G1 and G2, with adjacency matrices A1 and A2 and attributes X1 and X2, can we decide whether those two graphs are topologically identical? So topologically identical means that if we take one graph and then apply a permutation to its adjacency and accordingly to the node attributes, then we get the adjacency and the node attributes of the second graph, right? So basically up to indexing, reordering, the graphs are the same. Now, graph isomorphism testing has been studied like well before graph neural networks and graph machine learning became a popular topic. And it's known that there's no efficient algorithm for graph neural network, for graph isomorphism testing. So the only thing that we have are heuristics that can distinguish or that can tell whether two graphs are topologically identical reliably for a large class of graphs, but not for all graphs. So one such heuristic that's quite popular is the Weisfeiler-Lehmann test. I'm not going to be able to introduce the Weisfeiler-Lehmann test in practice, but it's a well-known heuristic that's been studied for many decades, and it's also known that it has some like well-known, very obvious modes of failure. So for instance, if you see here in the top row, you see two regular graphs, which of course we see that immediately are very different graphs, right? So for instance, G1 is a connected graph, G2 is disconnected. In G1, the largest cycle is 6, in G2, the largest cycle is 3, right? So very, very different graphs. But the Weisfeiler-Lehmann test would not be able to distinguish those two graphs, and in fact cannot distinguish any regular graphs, right? So what these two graphs have in common is that they both have degree 2 everywhere, so it's a 2 regular graph, and k regular graphs is something that the Weisfeiler-Lehmann test cannot distinguish. Now you might say, if we're talking about applications here, if this just arises with regular graphs, that's not a problem. But unfortunately, there are also non-regular graphs that are not isomorphic, and that the Weisfeld-Lehmann test would not be able to tell apart. So here is an example of two examples from biochemistry. Those are chemical structures of molecules. Even though again it's obvious to us that those are not topologically identical, the Weisfeld-Lehmann test would not be able to tell those apart. And now, unfortunately, so using this Weisfeld-Lehmann test as a reference point, it's been shown by Xu et al. And Morris et al. Both in 2019 that the expressive power, the representational power of a message-passing graph neural network is essentially identical to the Weisfeld-Lehmann test. So it's not more powerful, and there are certain message-passing architectures that are at least as powerful. But basically, if the Weisfeld-Lehmann test, or one could say that a message-passing graph neural network can distinguish two graphs if and only if the Weisfeld-Lehmann test can do that. So that also means that the failure modes of the Weisfeld-Lehmann tests are unfortunately also failure modes of message-passing graph neural networks. And once that's been realized, there's been a lot of interest in how we could overcome this limitation and increase, in a sense, the representational power of graph neural networks. And there's been quite a few proposals for doing this, including something called higher order graph neural networks, and various other modifications to the architecture that attempts to make the graph neural network more expressive. But one other recent line of work looks at what additional information we could give to the graph neural network to allow it to distinguish a larger class of non-isomorphic graphs. And if we think about what additional structure that could be, of course, a lot of graph characteristics come to mind, right? We could encode information about maybe the spectrum of the graph Laplacian. We could encode information about the node degrees, about counts of substructures, so various different graph characteristics. Our proposal is to give the network information about the curvature of the graph. We call this local curvature profiles. So basically what we do, again, as a pre-processing routine, is to compute the curvature of each edge in the graph. And then at each at input, we take the attributes of each node, and then to the given attributes in the input, we append some summary statistics about the curvature in the neighborhood of the graph. It's important to capture what is the highest and the lowest curvature locally. Again, as you've seen before, capturing those extremes is usually important. And then some other summary statistic in here. It's relatively robust to what summary statistic we are choosing, but something like the mean or the standard deviation, for instance, works quite well. If we use curvature notions such as like the approximate ORC curvature, Olivier curvature, or the Foreman curvature, then we can compute these local curvature profiles quite efficiently. So this pre-processing routine, again, is not something that takes a lot of effort, but something that can be done even for inputs of larger size. For message passing graph neural networks that are augmented in this way, so that have this curvature information given at each of the nodes, we can show that they're strictly more expressive, so can distinguish a larger class of non-isomorphic graphs than the Weisfeld-Lehmann test and message passing graph neural networks. I want to just illustrate this on one example that you see here on the right-hand side. So this is the 4x4 Rook and the Shikanti graph. Those are well-known graphs that are studied in combinatorics because they have some interesting properties that we're sort of are not super important for us here. What's important is that if we take different kinds of graph characteristics or information that we could encode about the graph, it's very hard to actually distinguish the two graphs. So they have the same degree everywhere. So if we compute, let's say, the degree distribution, this won't help us. They also have the same spectrum. So if we were to think to give it information about the spectrum of the graph Laplacian, for instance, as additional information, that would not help us to distinguish those two graphs. But they do have different curvature. So if we characterize their geometry with discrete curvature, in the case that I will be showing you here, it's Olivier's curvature, then we get different curvature, hence also different curvature profiles between like on a node level. And that means if we augment those graphs with local curvature profiles and then train a message passing graph neural network, we actually get representations that can distinguish between the two graphs. And why we get different curvature here is illustrated in the coloring. So for simplicity, we just look at the one edge here that's colored in red between U and V. And then I have colored the edges in the neighborhood of U in blue and in the neighborhood of V in green. Right, so let's say we again look at a uniform the distribution here to compute the Wasserstein distance. So we would put a mass of 1/6 on each of the neighbors, and we do that for both the blue and the green one. And then what I colored here in the thin red lines, those are edges over which we would have to transport a mass of 1/6 to transport the mass from the blue neighborhood to the green neighborhood. Okay, so the red edges here essentially show the optimal transport plan. And we see here that on the left-hand side, we just have to, it's optimal to just transport mass over these three edges, whereas over here, the optimal transport plan would require us to transport mass over many more edges and a mass of the same amount, 1/6, right? So that means that the transport plans between the two graphs are different, and hence also we get different curvature values. And the difference here, why curvature is able to capture the structural differences between those two non-isomorphic graphs, is because unlike node degrees, for instance, it can take information from the two-hop neighborhood into account and efficiently capture this in the curvature value. And this is not something that we can only theoretically observe on some sample graphs, but it actually makes a huge difference in practice. So again, showing here some experimental results. This is again this graph classification task that we looked at earlier. The different blocks here in the table are different kinds of message passing graph neural networks. And then in the top row, you always see the performance of the respective message passing graph neural network without any encodings. Then the second row here are spectral encodings. So if we encode information about the spectrum of the graph Laplacian, this row, for instance, is if we encode counts of substructures. And then the bottom row here is the one with the curvature information. And then we see that in almost all cases, at least for all graph classification tasks and in most node classification tasks, this gives the largest improvement. In particular, on graph classification tasks, we sometimes see an improvement of over 10%, which is quite massive for benchmark experiments like this. So this information that curvature encodes is really very crucial and helps the graph neural network to learn much better representations that also then translate into like real improvements in downstream tasks. Okay, and with that, I only have a few minutes left, but let me like very briefly talk about continuum limits of curvature. So far we have initially motivated how we define analogies of curvature in the discrete setting, that we sample to some extent the curvature that we have in the continuous setting. What we haven't really talked about is what the relationship between those two actually is. And in what way they are consistent, right, beyond just pure analogy. And we want to study this in the setting of geometric graphs. So geometric graphs you probably have encountered if you work with point clouds, or if you've applied manifold learning algorithms beforehand. The idea is simple. So suppose we have a point cloud with endpoints given in some space RD. We know nothing about the underlying manifold. So we assume that those points are sampled from a low-dimensional manifold, but we don't know anything about the manifold. We really have only the point cloud given. And then in order to construct a geometric graph, what we do is that each of our data points will become a node in our geometric graph. And then we consider an epsilon ball around each point, and we draw an edge between any two points that are within an epsilon distance. So like the center node at which the ball is centered will be connected to all other points within the epsilon ball. So for each sort of value of epsilon, we get a family of geometric graphs, essentially. Of course, the structure of the graph and the amount of sort of meaningful geometric information that can capture is highly sensitive to epsilon, right? You can imagine if we choose epsilon to be very, very small, then we have a largely disconnected graph that doesn't tell us anything useful about the structure in the graph. If we choose epsilon to be too large, then the graph is almost fully connected. And again, that doesn't capture any good information. But if we choose a good epsilon, and theoretically one can say what a good epsilon means, but for the sake here, let's say we have found a good epsilon, then the connectivity of our geometric graph should capture something about the true geometric structure in our point cloud. Importantly, we would like to measure distances, so construct these epsilon balls with respect to the Euclidean distance in the ambient space, right? We would sort of capture better geometric information in the graph if we were allowed to actually measure the true geodesic distances between the points on the underlying manifold. But since typically we don't know anything about the manifold, we don't really have access to that information. So the best we can really do is to compute the Euclidean distance in the ambient space. Okay, so that's a geometric graph. And now imagine that we were to sample more and more points, right? Get a denser and denser point cloud. And therefore also capture more and more of this underlying low-dimensional manifold from which our points come. So in this setting, we could, in principle, talk about a continuum limit, right? Where we sort of get a denser and denser sample of the manifold until eventually we approach the true underlying manifold in the continuum limit. So as we take more and more points, we can ask in what does the curvature that we can compute on this graph in some way approximate the curvature of that underlying manifold in the continuum limit. Okay, so those are the two key questions sort of that we're asking here when we talk about continuum limits of curvature. And we are interested in two particular questions, namely a local consistency. As we have said, I should say the curvature notion that we're considering here is Olivier's curvature. Okay, this does only hold. This is the one thing that only holds for Olivier's curvature, not for Forman's curvature. So we're comparing here in the discrete setting. We can compute Olivier's Ricci curvature, and then we compare that in the continuum limit with the true Ricci curvature, which is of course a local notion. So we can ask about local consistency. But then also sometimes, and I will give some examples later on, we are interested in, it's actually more interesting to know a global bound on the Ricci curvature of the data manifold rather than having a precise local characterization. So we can also ask about global consistency. So if the low-dimensional data manifold from which our point cloud is sampled, if that has a bounded Ricci curvature, is that something that we can measure in the geometric graph? So those are the two questions, local and global consistency. Now I want to say one more word here about the geodesic distances, right? So as I pointed out earlier, what we really can do in practice is only to measure Euclidean distances in the ambient space, right? We don't have access to the true distances on the manifold because we don't know the manifold. So for our analysis here, the best we can do is to try to approximate the geodesic distances from the distances in the ambient space. A slightly easier setting would be to actually say we have access to the true geodesic distances. And this is actually in most of the literature on continuum limits, this is the setting that people use. So they say that we have constructed this geometric graph and we have access here to pairwise distances of the true geodesic distance. But in order to actually apply that in machine learning, we really need to go to the second setting. So there's this important distinction between sort of what's done for any kinds of continuum limits in the classical literature and what we really need in order to apply continuum limits in practice. So what is known about continuum limits? So for the curvature, as we said, we're interested in local and global consistency. And there's been essentially nothing known about these consistency results before this work. There's one result in setting 1, so assuming access to the true geodesic distances, that gives an asymptotic result on local consistency by van der Hoorn et al. So that basically says that in the continuum limit, so with infinitely many points, essentially we recover the true Ricci curvature, but it cannot give us an error bound of what kind of approximation to the true Ricci curvature we get with n points, right? But in order, again, to use this in practice in a machine learning setting, we would really like to have these non-asymptotic error bounds where we can say, what is the local and global approximation of the curvature that I get with n data points with a point cloud of size n. These kinds of non-asymptotic continuum limits have been studied for other graph characteristics, just not for Ricci curvature. So for instance, for the graph Laplacian, their results there go back to the early 2000s, Hein et al., and then also recently a nice paper by my co-author on this, Nicolas Garcia-Trias and Jeff Calder. And there's also been a lot of work on understanding approximations of geodesic distances. So if I just measure the Euclidean distance in the ambient space, and I want to recover the geodesic distances on the manifold from my geometric graph, what sort of non-asymptotic consistency results I get there, that is also something that's been quite well studied. So as you can probably tell from my speech here, we were able to show local and global consistency results. Importantly, we were also able to show this in the sort of more realistic setting too, where we really only require access to Euclidean distances in the ambient space. And this is informally stated the kind of result that we get. So here we have the curvature computed on the geometric graph, and then the Ricci curvature of the corresponding point on the underlying manifold. And then we see here we get a non-asymptotic bound, so we can say something about little n here is the number of data points, so we can say precisely what kind of error we would expect with n data points. And then, of course, there's a dependency on choosing the neighborhood radius right, but we have some analysis of that in the paper as well. We have a dependency in the error bounds on the dimension, of course, and then also some approximation error that comes in when we approximate the geodesic distances from the ambient Euclidean distances. But we have a good characterization of what that error is, and we can show that, in fact, we can recover a local characterization of the Ricci curvature of the data manifold by computing Olivier's curvature on the geometric graph that we have constructed from the point cloud. And then perhaps for machine learning applications, even more interesting is that we get a global consistency. So if our data manifold has a bounded Ricci curvature, and let's say it's bounded by a constant k, then this constant k we can also learn from the curvature that we compute on the geometric graph. And again, we have a non-asymptotic bound on this that can give us some guidance on what the kind of approximation is that we can get with n data points. And then I think I'm technically out of time, but I want to just, if I can get 2 more minutes, I just want to briefly talk about where these kind of results could potentially be applied. So it's been mostly a theoretical work. If you're interested in reading it, we discussed a little bit potential applications in spectral graph learning, but I think there's a lot of other applications in the machine learning context that arise here. So in particular related to applications in representation learning. So there's a lot of interest and also been a lot of work for decades really on understanding the geometric properties of data manifolds. So manifold learning algorithms such as MDS or ISOMAP, for instance, give us an implicit characterization of the intrinsic dimension of a data manifold. And then more recently, there's also been interest in approximating curvature from data. So for instance, there's a really nice work by Amari and Lefrard that look at extrinsic curvature, so approximating the second fundamental form. What this here gives us is a way to approximate intrinsic curvature, Ricci curvature from data. Which in a sense maybe is complementary to the kinds of characterization that we get from manifold learning algorithms, for instance, and from these other ways of approximating curvature. So I think there's a lot of potential in applying those methods in the representation learning context. And then I want to mention, yes, I want to just skip to that. Another recent line of work in my group is to try to understand how the characteristics of a data manifold have implications for how efficiently we can train neural networks on such data. So Soledad mentioned some work related to generalization and sample complexity yesterday already, and I think there was also a question from the audience related to trainability, PAC learning type guarantees. We don't use PAC learning here, but SQ learning, which is a sort of a special case of that characterizes learning with or training with gradient descent, right? Which is sort of sufficient in this context because we usually train graph neural networks with gradient descent. And it's been shown that standard, shallow, fully connected neural networks cannot be efficiently trained. So there's a computational hardness there, a potential exponential dependencies on the kind of effort that goes into training those networks. And we've shown in a paper that came out earlier this year that if we encode symmetries as an inductive bias, so use equivariant neural networks, the kind of architecture that Soledad introduced to us yesterday, that those kind of inductive biases are not enough to overcome these fundamental limitations. But yet in practice, neural networks training of neural networks usually works quite well. And what we've recently shown is that actually if we take into account that data usually lies on a low dimensional manifold, that there are settings where we can provably show that you can train neural networks efficiently. And one of these settings where we can actually certify that that is the case is for manifolds that have a bounded Ricci curvature. So if we can evaluate sort of a training data set or the underlying manifold from which that training data set was sampled, and we can learn with tools such as the continuum limits of Olivier's curvature that I've just shown you, that could give us a hint of how the geometry of our data looks like, and then get an idea of what kind of behavior we, for instance, expect when we train a model like neural networks in that setting. Okay, and with that, I'm over time and I'm coming to an end. So just to briefly summarize, we discussed different notions of discrete curvature in this talk. We discussed how we can define such notions via curvature analogies. We talked about curvature-based rewiring and encodings and how that can help us to improve the efficiency of graph neural networks. And we talked about Olivier's curvature on geometric graphs, continuum limits, and the local and global sense of Olivier's curvature, and then also some applications and implications for machine learning on such structured data. And I want to just briefly acknowledge funding and then also the main co-authors here. So Lukas Fesser is a PhD student with me at Harvard. He's the main co-author on the work related to graph neural networks. Nicolas Garcia-Trias is the co-author on the continuum limits. And then Bo Bakiani is a postdoc in my group who led the work related to the learning complexity of neural networks. Thank you very much.